Well, now we're ready to use all of this new information that we have. And let's use it first to calculate at 25C the value of delta G for our reaction N2O4 going to NO2, which we know under standard conditions has a value of plus 5.3. But what's the value of delta G at 100 Celsius, or 373 Kelvin? Well, we know exactly how we can do this. We can calculate the change in free energy at 373 Kelvin under otherwise standard conditions. That's going to be equal to delta H at 298 under otherwise standard conditions minus the temperature times the change in entropy at 298. That means that I can look up these thermodynamic variables from any table, and it means that I can calculate now delta H for this reaction, and I can simply plug in the values because I have 2 times delta H for NO2 minus delta H, this is delta H of formation, of N2O4, and by plugging in the numbers I get 57.9 kilojoules for the equation as written. Okay, I can do exactly the same thing for delta S. I can take those directly out of my thermodynamic table, and I get 177, in this case, joules per Kelvin. But now I use this remarkable simplification that I can calculate delta G now at 373 Kelvin under otherwise standard conditions, and that's equal to 57.9 kilojoules. And then I have a minus 373 Kelvin. I have to be careful to convert this to kilojoules, so that will give me 0.177 kilojoules per Kelvin. And that gives me a delta G of minus 8.1 kilojoules. So now we redraw our free energy surface. We know that we're starting from reactants and going to products, but now we have a delta G of minus 8.1 kilojoules. And so what we have done is to increase the temperature from room temperature to 100 degrees Celsius, or 373 Kelvin. And that means that we have now connected our calculation of delta G quantitatively, and we can look at the analysis of why did this reaction equilibrium shift to the right when we increased the temperature. That is, why did it shift from pure N2O4 to creating more NO2? Well, let's go back to our reaction coordinate, converting N2O4 into 2NO2. Well, when we analyze this, we know that the overall reaction is endothermic. That means it requires heat to drive it. So I can write this as N2O4 going to 2NO2 minus an amount of heat to make up for the change in enthalpy of that reaction. Well, that's interesting. I've just increased the temperature. I've shifted the equilibrium from left to right. I've increased the amount of NO2 in that equilibrium, and this is exactly what Le Chatelier would tell us, because when we're driving from N2O4 to NO2 by putting temperature in, this reaction is trying to compensate for that by extracting heat from the system that's required to drive the endothermic character of that reaction. So we now have a connection between our calculation of Gibbs free energy, the equilibrium constant K, and the principle of Le Chatelier.